Singla. He's a professor at Georgia Tech. He graduated from CMU a few years ago and then spent a few years at Princeton and the Institute of Advanced Studies. And then he moved to Georgia Tech. Sahil has interests in algorithms under uncertainty, which is the topic of our workshop today. And as you saw yesterday, if you have an open question, there's a pretty good chance that Sahil already knows the answer. So with that, over to Sahil.
Thank you, Debmale. I hope everyone can hear me. Yes, great. Hello, everyone. Yeah, so today I'll be speaking about some online and Bandit algorithms. So I'll get into the problem details in a bit. But this is based on joint work with Thomas Kesselheim from University of Bonn and Marco Molinaro from Rio. And I think Marco is also spending some time at Microsoft these days. Good. So let's get started. So the talk is broadly about online and Bandit algorithms. So we have a result on both the settings, but here I'll mostly focus on the online aspect, and towards the end I'll mention what kind of guarantees we can show for Bandit problems as well. So here's the broad level again. I mean, I know all of you've seen online algorithms, but to recall, you have T requests arriving one by one. As soon as a request arrives, you need to immediately serve it. And I mean, we'll be focusing more on like combinatorial problems, say, such as like load balancing, facility location, set cover, sanitary, and so on. And often in many of these online problems, the goal is to minimize some kind of a norm objective. So to think of like, say, load balancing, often you're interested in things like the L infinity or the make span minimization, facility location, set cover. Like all of these problems, often you can think of them as you're minimizing some cost, which can be thought of as some kind of a norm or length. And the two extremes are, one is the L infinity norm, which sometimes you think of as the egalitarian. You want to minimize the max cost. And the L1 is more like the sum of the cost, so you want to minimize the average cost in some sense. And LP norms people often think of as some kind of an interpolation between the two extremes. And okay, so we've been studying this like online problems for like 4 decades or maybe even longer, and we have like lots and lots of results. But often people have been focusing only up till LP norms. And I mean, people have been designing these guarantees in terms of competitive ratio. Like, how can we show a good competitive ratio, a small competitive ratio, closer to a constant? Maybe if the constant is not possible, maybe a logarithmic guarantee. And yeah, so we have lots of results for LP norms. But our focus has been more like, okay, can we generalize this objective beyond LP norms? Like, what about more general norms or more general convex functions, object cost functions? Till what settings, in some sense, we can get some guarantees, good guarantees. Okay, so that's the high level spiel. Like in some sense, yeah, the focus is how much can we generalize the objective function class while still obtaining good guarantees. Good. So the running example in today's talk will be the load balancing problem. So this is the classical online problem. So for some of you who know the experts in the setting, it's the unrelated machine setting. But what it's happening is you have capital T jobs arriving one by one. Capital T, think of it as the time horizon. Each time step, a new job arrives. Whenever a job arrives, you have D machines. So these are not identical machines, these are just D machines. And the incoming job tells you how much time I'm going to take if you schedule me on one of these machines. So a bit more formally, like when the Tth job arrives, it reveals you a vector, a D-dimensional vector, where the ith entry tells you how much time this machine is going to take on the ith machine. And you need to find a schedule, which basically just means like on which machine you're going to send this job, so as to minimize some norm objective. So what do I mean by norm objective? So look at the load vector. Like, so each machine has some total load in the end. Like the jobs that go to that machine, sum up those costs. So you have like these D dimensional because you have D machines. That's why I'm calling D machines, because D is also the number of dimensions. So for this load vector that I have, like for each machine, ith entry is the load on the ith machine, I take some norm. And so for instance, like the classical settings, special cases of this problem have been studied like since at least the 60s, like say more than 50 years ago. But L infinity norm is the classical make span minimization setting, where you want to minimize the load on the machine, which has the maximum amount. And we already know that although constant approximations are not possible, constant competitive ratios are not possible here, but you can get a logarithmic competitive ratio. And EOC is in, probably in the audience, yeah. So these are like results like say 30 years ago. And so these are like really classical fundamental results in online algorithms. And also like not just L infinity norm, even LP norms have been studied roughly like say 25, 30 years ago. And we know roughly order P competitive ratios are tight. So if P is like more than log D, then you might as well like basically just, you can always bound P by log D, the L infinity. Good. So this is well understood. So that will be the running example in today's talk. So if something is not clear, yeah, do question me. Yeah, so towards the end, I'll mention like some other results on other problems as well. But basically, to keep things concrete, I'll just focus on this problem, this simplest looking setting. Like, yeah, just job comes, you just schedule it on one of the machines. And eventually you have some D loads on the D machines and you take some norm of it. Good. Okay, so the question is that, okay, can we get some small competitive ratio for more general norms? Like ideally maybe logarithmic. So we cannot hope to get a constant because already for L infinity you cannot get a constant. The best you can hope for is like a logarithmic in D. And the question is, can I get logarithmic? So another thing I want to stress on is like usually in all these problems, usually getting poly D is easier. Polynomial in the number of dimensions because pretty much all norms are equivalent up to polynomial factors, poly and D factors. What's interesting is if you can get something like logarithmic, which scales like much slower in the number of machines. Good. Okay, so we'll be interested in this setting. And okay, let me make something more concrete, like what do I mean beyond LP norms? So let's first recall what's the definition of a norm, or we'll be interested in monotone norms. By monotone norms, I just mean like if you increase a coordinate, the length can only increase. I mean, you might wonder like all norms are monotone, but no, I mean, the mathematical definition of norm, it is possible to construct even non-monotone norms, but we'll be interested in just monotone norms because for our applications, that's the one that makes sense. And we'll be only interested in the positive orthant because the loads on the machines are all non-negative. So let's recall the properties. So the first three properties are standard, like you have homogeneity, the second is the triangle inequality, and the third is just that if the norm is 0, the vector has to be 0. And the fourth, as I'm saying, is monotonicity, that if you increase the coordinates, the norm can only increase. So this is in some sense the largest class of norms for which you can hope to prove, say, good competitive ratios. So like ideally you want to obtain a logarithmic competitive ratio for arbitrary monotone norms. Good. So unfortunately, we still don't know how to achieve it. So that will be like my open question on the last slide. But we'll be focusing on a subclass, which is still quite general. These are monotone symmetric norms. So it's again an arbitrary monotone norm, but by symmetry, I mean it's invariant to renaming the coordinates. So if tomorrow I start calling coordinate 2 as coordinate 5 and coordinate 5 as coordinate 2, if I do any of these swaps or something, the norm should not change. Okay, so this is known as a monotone symmetric norm. And to give you a few examples, first of all, LP norms are all symmetric because, I mean, if you rename the coordinates, it doesn't matter. And then there are generalizations of LP norms to things called Orlick's norms, where instead of working with functions like x to the p, you work with some other convex functions. Another important object, which will be important like in this talk as well, is the top k norm. So by top k norm, I mean if I give you a vector, you just look at the sum of the largest k coordinates. Okay, so the largest k coordinates, and remember all our vectors, we'll be interested in only non-negative vectors. So everything is non-negative, so we don't have to worry about how to handle negative entries. Okay, so just I want to sum up the largest k entries, and notice that top 1 is nothing but again the L infinity norm, and top D is nothing but the L1 norm. But top k is in some sense like, yeah, you can again think of it some kind of interpolation, and then there are generalizations of this top k norm to ordered norms. There are other many operations you can perform which preserves symmetry. For instance, you can take like non-negative linear combinations, compositions, and a bunch of other things you could perform. So this is a very rich class. It captures many forms of norms and all. So the question is, yeah, what can we do for these monotone symmetric norms? And it's not just us. Like there's been actually a lot of recent work on designing optimization algorithms for these monotone symmetric norms, but mostly in the offline setting. So all these works, starting at least since like Chakrabarti Swami 2019, but even before, they've mostly focused on offline settings of these problems. For instance, I ask you the same load balancing question. What can you do offline? Can you still design good approximation algorithms? But here the challenges are a bit different because offline you're only interested in getting you really want to get a polynomial running time. Because if I give you infinite computation, then you can always solve the problem for any objective. You can just brute force everything. So online, on the other hand, the challenges is more information theoretic because I don't even know the future. And so somehow like the techniques need to be a bit different. Is that clear? Yeah, please do ask questions. Yeah, I do want it to be interactive. Yeah. Okay, so the main result, as you might have already guessed roughly by now, is that there is a log square D, so we get a polylog approximation, a polylog competitive ratio for this online load balancing problem for monotone symmetric norms. Okay, so we have monotone norms, and the additional thing we need to assume is symmetry, and then we can get a log square competitive ratio. And as I was saying, there's already a log D lower bound for the L infinity norm. So you can hope to improve our bound from like log square to a single log, but not to a constant. And the techniques do generalize to a bunch of other problems. There are generalizations of load balancing. There are like problems related to bandit problems. Some of that I'll mention towards the end, but I wanted to give a concrete example here. And although running time is not the primary focus, but turns out our algorithms can also be made polynomial in running time, given appropriate access to the norm. Like a general norm is a very general object, so you'll have to formally define what kind of access do you have to this norm. So if you have some kind of a ball optimization access, like where you can optimize some linear function on a unit ball, then you can make these algorithms even polynomial time. But yeah, I guess the most exciting thing is even information theoretically, can you do a good competitive ratio? Okay, any questions? No. So if not, like, so the high level proof idea goes via, in some sense, like 2 steps. The main thing is we introduce something, this notion of gradient stable approximation. So it's some kind of a, you can think of like some kind of a smooth approximation of the original norm. And what we show is that as long as your norms admit some kind of a gradient stable approximation, then you can design good algorithms for load balancing problems and some of these other problems. And so the step 1 is basically we introduce this notion and why it suffices. And step 2, you can think of it as how do we show that actually symmetric norms or some of these other norms, they do admit these gradient stable approximations. And the building block will actually be somehow we'll first design gradient stable approximations for the top K norm, the norm I mentioned just a couple of slides ago. And then we'll use some norm composition theorems to argue that actually arbitrary monotone symmetric norms also admit gradient stable approximations. So that's the high level thing. So here's the outline for the rest of the talk. Like I talked about, introduce the problem, and now I'll first introduce this notion of gradient stable approximation and why it suffices for load balancing. And then I'll be designing gradient stable approximations for symmetric norms. And finally, I'll conclude with some extensions. Okay, next. So this part, let's focus on this first part, like how you can solve load balancing problems using this notion of gradient stable approximation, and which goes via some kind of a smooth game inequality. I'll mention what that is. Okay, so let's first actually look at the greedy algorithm. So often, like greedy algorithms are just like they appear a lot in online algorithms. Sometimes you run them directly, sometimes you run them in after adding a regularizer or something else. So greedy algorithms are actually very powerful, and actually we do want to run some kind of a greedy algorithm. But the naive greedy algorithm you might attempt, like the first greedy algorithm you might think of for any of these scheduling problems, is just to, so suppose you've already made decisions till time step t-1, you have to make a decision for the tth step, you'll choose, like send this tth job to a machine such that your total load, like this norm of your load vector, that's minimized. So lambda t-1, my notation is that's the load till time step t-1, and I'll choose this yt. Basically, yt is basically, it will have zeros in all coordinates except the machine where you send the job. And so I want to choose yt in a way that the total length is minimized. So that's the greedy step. But turns out already for the L infinity norm, this greedy algorithm can be bad. It gives you like a omega d competitive ratio. And recall, like poly d is bad. I mean, we want like polylogarithmic at least. Okay, and this was already shown again in the 90s. And okay, so naive greedy does not work. And this is something you might have seen other places as well. And so what often happens is you work with some kind of a smooth approximation for your algorithm, like for your objective. So rather than running the greedy algorithm on the original norm, run it on some kind of an approximation psi of the norm. So think of this psi as nothing but some well-behaved approximation of the original objective, original norm. Good. So this is what I'm going to be calling like, so the question will become basically what are the right properties that I need from this function psi while making sure that psi is close to my original norm. Okay, so that will be the high level, and our algorithms will precisely be this, like we'll be just running a greedy algorithm on this function, on this well-chosen function psi. Good. So, okay, to begin with, like so things like L infinity norm, you might have seen, like, I mean, a common approximation for L infinity norm is just the softmax function. And actually that does work. So for the L infinity norm, if you just work with the softmax function, which is nothing but the natural or like log of the sum of the exponentials, that has very nice properties. First of all, like it approximates your original norm up to an additive log d. And one can show actually that one can actually reinterpret the proofs of the original paper as well, that actually this gives you a log d competitive ratio. So there's nothing fancy, and some intuition to keep in mind are these contour plots. Somehow, like if you think of the max function, that has these sharp corners around when, like, say, if you're already in 2 dimensions, when the first 2 coordinates become very close to each other, then you have like these sharp corners. Whereas softmax function has like it's more rounded and well behaved. So I mean, yeah, pictures can be misleading, but still to give some intuition, when you want some nice properties of this psi, like the C of psi function, which is the approximation, which has these more well-behaved gradients, and that's what we'll be getting into. Okay, but for L infinity norm, already like just running the greedy algorithm on this softmax function is a good idea, and this was already known since the 90s. So at a high level, the question is, what's the right notion of smooth greedy for general norms? For more general norms, what's the right way to round these norms? Good. Okay. So now I'll go over a bit of the analysis of the greedy algorithm. So as I'm saying, like what we want to run is the greedy algorithm on this psi function, which is some kind of an approximation for your original norm. Good. And so yeah, what I'll be presenting is, I mean, in some sense, things like this have appeared in the past as well. But so people have in the past like mostly analyzed such results for some concrete functions psi, like for instance the softmax functions. There it becomes less clear what all properties, what is in some sense the minimum set of properties that you need to be able to prove some guarantees. And hence to some extent we are giving like a different interpretation of the older proofs while trying to minimize the set of properties that we need. Okay, so how do I analyze such kind of a greedy algorithm if I'm running on the psi function? So think of psi function as nothing but pretty much the norm of your load vector up to some additive and multiplicative approximations. Okay, so I'm really interested in what's the psi at time step capital T, like in the end. So let's look at the total change in my function psi of lambda capital T minus psi of lambda 0. So the norm of in the initial is just the norm of the 0 vector, which is 0, but psi of 0 need not be 0, so you have to be a little careful about handling these 0 terms as well. But think of psi of lambda 0 as nearly 0. Okay, so and psi of lambda t roughly represents like it's close to the norm of the lambda t vector, which is roughly your alg. So this can be thought of as nothing but sum over all the time steps that change in this function. And because each time step I'm performing the greedy thing, so I can always replace this, whatever choice my algorithm is making at the tth step, it had the option of sending this tth job at the machine where the optimal schedule is sending. Like, so look at the offline optimum, the hindsight optimum. Whichever machine this tth job was sent to, my algorithm could have also done the same choice. So I have this inequality. Like the increase in my algorithm is at most the increase of if I was making the optimal choice at this step. So this first inequality just follows from the greedy step. Okay, and then comes the second inequality, which so yeah, I'm not proving it right now. I mean, the rest of the talk will be actually why this inequality holds, something like this holds. But this is known as something called as the smooth game inequality. But I mean, I'll get to the name a bit later. But roughly what you want to say is that you want to bound some of the differences of like these opt, like when you're performing this y star t, by some constant times opt plus another constant times alg, plus some like psi of lambda 0 terms, but think of them as like roughly 0. So they don't matter too much. So all you want to do is like you'll want to look at the one-step differences of performing these optimal actions for all the time steps. You want to upper bound that by some constant times opt plus another constant times alg. And why such a thing will suffice if you have somehow magically such an inequality is because then now you can rearrange the terms. You will basically get like psi of lambda t, which is roughly your alg's total cost, is at most some constant times psi of lambda star, plus again some psi of lambda 0 terms, which you can think of 0 as like nearly 0. So you basically have like a constant approximation or like whatever are these parameters C1, C2 and so on. So yeah, so all I'm saying is this is like another way of interpreting the greedy algorithm, the analysis of the greedy algorithm for a more general function psi. So all you need is first the greedy step followed by this smooth game inequality. And that will already be finished. I mean, that will complete the proof because you can just rearrange the terms and that allows you to bound psi of lambda t, which you want it to be roughly close to the value of the algorithm. The reason I'm calling it the smooth game inequality is because related notions have appeared in algorithmic game theory for the analysis of price of anarchy. So in price of anarchy, once you reach like some kind of a Nash equilibrium, you have a bunch of agents. No agent has any incentive to deviate. So one way of analyzing some algorithms is you see like at equilibrium, what happens if each person tries to deviate to something else. And you want to control the sum of the deviation. So there also, like in those kinds of analysis, you again get things like at equilibrium, if each agent tries to deviate, like deviate from yt to y star t, like something else, like from, then those deviations should be kind of bounded. They should be bounded by something like a constant times opt plus a constant times alg. So similar notions have appeared before, but in a different setting. But turns out like R inequalities can be also thought of at least at a high level as having a similar framework. So the question is, when do such an inequality holds? Because once you have such an inequality, then yeah, you're in a good shape. Any questions? Yeah.
So the standard analysis for the infinity norm, what it does at this point after the first inequality is just add the opt into both sides, right? So is there a way of interpreting that in terms of what you wrote here?
Yeah, so yeah, if you add the opt there, yeah, so that gives you, yeah, so I mean, basically you use some properties that I'll be mentioning, like when does such an inequality hold? So yeah, I agree with you. Previous analysis have usually written it in this way. And so we had to kind of reinterpret it, like what is in some sense the least set of properties that you need. And yeah, so maybe it will be more clear on the next slide. Okay, so yeah, the main thing I want to say is like such a thing is what we need. Good. So, okay, recall, like I want to prove that such a smooth game inequality holds. And the question is, when does such an inequality hold? And the lemma here says that as long as your function is monotone subadditive, like standard properties of norms, and some supermodularity assumption, I'll define what this supermodularity is. But as soon as you have this supermodularity and this monotonicity and subadditivity, then the smooth game inequality holds. Okay, and I'm cheating here a little bit, like when I say less than squiggly, less than equal to, I mean like I'm hiding some constants. Like there are some multiplicative constant factors. Good. And what's approximate supermodularity? It's, as you might get, it's basically supermodularity up to some constant factors. So what's supermodularity is like once you add something, so like if you add vector y to your current load lambda, the increase in the function psi is at most if you add again the same vector y to a larger load vector. Like rather than adding y to lambda, add y to lambda plus z, where z is all non-negative, everything is non-negative. Then the increase should only be larger, like the change in the function value should only be larger. So, and I'm calling it like, so this is the standard supermodularity, but because I'm using squiggly less than equal to, that's why I'm calling it approximate supermodularity. Okay, so the claim is that as long as you have some kind of approximate supermodularity, you can have a smooth game inequality. And often like these proofs which go like by adding opt and so on, they use some kind of this supermodularity kind of inequality, like as Demale was asking. Okay, so why this suffices, why the lemma is true, it's actually pretty short, like I mean, but I'll just only flash the 2-3 inequalities. But basically you have to just apply this approximate supermodularity on like some carefully chosen two functions and sum up the inequalities. So basically it's just these 3 lines. You apply approximate supermodularity twice on these appropriately chosen functions, where you are basically doing, as Demale was kind of suggesting, like you kind of add this opt term or like y star t, and yeah, then you sum it up and so on. So, but the crucial thing, I guess, let me just even hide the proof, is that this approximate supermodularity is the crucial thing. And it's kind of counterintuitive because actually norms do not satisfy this. But because we are not working with the original norm, we are working with some kind of an approximation for this norm, then you can hope to prove such a thing because I'm allowed both like additive approximation and multiplicative approximations. Good. So the thing is, we just need approximate supermodularity. Okay. So, and what the next slide, the slide 10 says is like, this is where gradient stability comes. So like the definition I'll explain in a second. But what we'll claim is that this gradient stability suffices to prove approximate supermodularity. So if your function psi has gradient stability, then it implies approximate supermodularity, and approximate supermodularity implies the smooth game inequality, which implies that the greedy algorithm works for your load balancing problem. Good. And what's the gradient stable approximation? So the gradient stable approximation is just that you approximate your original norm by some function psi, which has the following properties. So properties 0 and 1 are standard. Like 0 just says that your function needs to be, again, monotone, subadditive, convex. 1 means it has to be an approximation of your norm, like some alpha multiplicative and gamma additive. I mean, it's an approximation for your norm. The crucial thing is this property 2, the stability, which roughly says that the gradient of your function should not decrease too much if I add some load. So let me repeat this. So you look at the gradient of this psi function at lambda plus z and compare it to the gradient at lambda. So roughly you want to say, like, if I increase my coordinates, the gradient in general could decrease. It could, I mean, in some coordinates it could decrease. Notice your norm will always increase, but the gradient could decrease. So what this inequality is saying, that the gradient should not decrease drastically. It can drop small amounts. Like if your change is a lot, then of course it can drop a lot. But if your change is small, then the gradients cannot drastically drop. I mean, related notions people have studied before as well, like something called monotone gradients, where the gradients have to just increase. But here we are saying, like, okay, it need not increase, but it has to be like roughly kind of, in some sense, non-decreasing. Okay, and then once you have this, I mean, to give you some examples, like, okay, for L infinity norm, again, one can show that softmax function satisfies this. For LP norms, again, there are like standard ways of designing things. I mean, the question is, how do we have gradient stability for more general norms as well? But for LP norms, like what standard constructions can be verified to have this property of gradient stability. And as I was saying, like related notions have been studied before, not exactly in this sense, but for instance, like monotone gradients have been studied before, and there are other settings as well. Good. And the main lemma, as I was saying, was that once you have this gradient stable approximation, it's a simple one-line proof that why this implies approximate supermodularity. So you just take the appropriate integral, and so that gives you approximate supermodularity. And yeah, so the main takeaway from this part of the talk was, from this section, basically was, you started off with the load balancing problem, the leftmost, where you're trying to schedule these jobs on these machines. We wanted to analyze the greedy algorithm on some psi function. And what we showed is that as long as this psi function satisfies this smooth game inequality, which has like a similar flavor to this price of anarchy literature, then you are done. And what we show is that, okay, approximate supermodularity suffices to show the smooth game inequality, and approximate supermodularity status follows from this gradient stable approximation. And what's gradient stable approximation? It's basically this, in some sense, you need the convexity and all those assumptions, but besides that, it has to be an approximation. Property 1 and property 2 is that the gradient should not drastically decrease. Okay, any questions? And yeah, so the remaining part is, how do I design these gradient stable approximations beyond the LP norms? Okay, so let's continue. Yeah, so now how do we design these gradient stable approximation? And as I was mentioning earlier, like the way it happens is, we'll first design a gradient stable approximation for the top k norm. So top k is nothing but the norm where you sum up the largest k coordinates. And then we can apply some norm composition theorems to extend these to get a gradient stable approximation for any monotone symmetric norm. So the takeaway from this other part will be like, okay, first of all, how do you design gradient stable approximations from top k norms? And then a good high level message to keep in mind is that once you can do top k norms, often those techniques can be generalized to any monotone symmetric norms. So there are like some standard reductions, standard or like standard ideas at least. Okay, so and first let me say like how symmetric norms can be thought of as nothing but some kind of a composition of top k norms. And so first of all, these connections go quite back. For instance, what's known is that if you have two vectors and like the top k norm and y kind of dominates x, in the sense that if I look at the top k norm for every k, y has a larger top k norm, then the symmetric function, like then the norm only increases. And this follows from like Schur convexity, fan dominance theorem, like there are multiple names for this and like generalizations of this result. But I mean, yeah, this is only just to, like if you've heard any of these names, then to tell you, but there are, all I'm trying to say here is that top k norms have close connections with monotone symmetric norms. As long as you have symmetry, then top k norms are a good kind of surrogate. And in fact, you can formalize this like the kind of lemma we'll need in our work is that any monotone symmetric norm can be actually approximated up to like a logarithmic factor, logarithmic multiplicative factor, by max of a bunch of top k norms. So I give you like rather than, so any monotone symmetric norm can be thought of as nothing but max of a bunch of top k norms, of like logarithmic many weighted top k norms. I mean, top k norms multiplied by some weights. And this is again like to give you a high level proof why such a thing holds. Again, like I mean, the intuition is actually very easy. The intuition comes from that any norm can actually be thought of as nothing but a max over a bunch of linear functions. So the high level intuition is that any norm, because of its dual representation, can be thought of as nothing but a max over a bunch of linear terms. And because you're working with monotone norms, these linear functions are also like non-negative and so on. So once you have this, a bunch of max over a bunch of linears, using standard powers of 2 trick, you can imagine all these weights are in some polynomial range and they're only like powers of 2. So you have roughly like logarithmic number weight classes. And okay, up to losing a logarithmic factor, I can just focus my attention on a single weight class. And now you're in kind of in an unweighted setting. And in the unweighted setting, a symmetric norm is basically nothing but a top k norm. Because you are allowed to take any permutations, and that basically gives you nothing but a top k norm, up to like multiplied by a constant. So that's the rough intuition why any monotone symmetric norm can be like up to some log factors, thought of as like a top k norm. Good. So, and this is also the reason why we'll eventually get a log square approximation, because we lose one log factor to reduce a monotone symmetric norm to a single top k norm. And now for a single top k norm, because it captures L infinity as well, we lose another log. Any questions? Okay, yeah. So let's now try to design, like we want to design this gradient stable approximation for the top k norm. And recall the property I want is somewhat that the gradient should not drastically decrease. So the gradient of lambda plus z should be comparable to the gradient of lambda up to some factors. And think of z as small, like the vector z. So the first idea might be to just, okay, try out directly the norm. And that fails, I mean, because of standard reasons. I mean, here's like one concrete example. Like you have your original vector, the first coordinate is epsilon, everything else is 0. You change it slightly to epsilon comma like 2 epsilon everywhere. So you've slightly increased the vector, but the gradient, like the coordinate, the first coordinate of the gradient drastically changes. It was originally nearly 1 because this coordinate was in the max in the top k norm, and now it has gone to pretty much 0. Okay, I mean, some other ideas you might try is like adding noise, similar to like follow the perturb leader and those kinds of ideas. So again, it's, I mean, and one common idea of adding a noise here is to add like an exponential noise in each of the coordinates and then take the top k norm. So, but again, it's possible to construct examples where such a thing does not work. So what actually ends up working for us is kind of like a exponential noise again, with one more idea that you don't take the top k norm for the k that you have in hand, but take a random k. So in particular, you choose a capital K from some geometric distribution where the expectation is the small k. So your function, the psi function that we eventually work with, is the expectation of x plus nu, where the expectation is over both the random capital K that we are choosing and the noise nu that we are adding. And I'm going to take the top k norm of this, top capital K norm of this. So what can be shown is that, okay, once you have such a construction, I mean, yeah, it's a bit hard to give why this works, but it's a bit hard to give the intuition. But what can show is like, I mean, this simple looking construction actually now satisfies both our gradient stability properties. First of all, it's a good approximation for your norm. And secondly, and crucially, it satisfies the stability property that the gradient does not now change anymore drastically. And as I was saying, like once you have this gradient stable approximation for top k norms, you can combine it with the norm composition theorems that we had like from last 2 slides. And that basically gives us a gradient stable approximation for any monotone symmetric norm. And so again, the main takeaway here is that you have a log square D approximation here for this load balancing problem. And the way we went is that we started off with the load balancing problem. We analyzed the greedy algorithm, which works as long as you have the smooth game inequality, which holds if you have approximate supermodularity or the gradient stable approximation. And this gradient stable approximation can be designed via norm compositions applied on top k norms. And so let me now finally just conclude with some further results and extensions, unless there's a question actually. Yes, yes.
I assume that since your algorithm consists of two parts, you have an example for certain norm that you lose the log square thing for your algorithm.
No, actually, so it's possible that for my algorithm, probably, yes. For our algorithm, I mean, we haven't written it concretely, but I think we can construct an example, yeah. For our algorithm, like the kind of approximation we do. Because in some sense, we are getting log square, as I was mentioning, like one is just a naive approximation of your symmetric norm by a top k norm by a log factor, and the other is, you have to lose the second log as well for a single top k norm. Any other questions? Okay. So if not, then I will maybe just conclude with some other extensions and open problems. Okay. First of all, let me say first, like these results also extend to a few online problems. There are generalizations of online load balancing. For instance, one generalization is whenever the Tth job arrives, you have say, like rather than just scheduling it on one of the machines, you have maybe say k or some parameter k, say k options. And depending on what option you choose to finish this Tth job, it might incur some load on all of the machines. So there are generalizations of this form. Like these are known as like some generalized load balancing problems. So our results extend to these problems as well, and there are some other applications which we discuss in the paper. But in the next slide, let me just briefly mention connections to some bandit problems. In particular, there's a strong connections to this so-called bandits with knapsacks problem. So what's the bandits with knapsack problem? And this is like a problem which was introduced at least 10 years ago by Ashwin, Bobby Kleinberg, and Alex Slivkins. And so it's similar to the classical bandit problems where you have, say, capital K fixed actions. Each time step you take one of the actions. The action you take is going to give you some reward, and you have a bandit feedback. So you want to just maximize the total reward. The additional part is that each time step you take an action, not only it gives you a reward, it also incurs you a vector cost. Okay, so the first step is saying that, okay, you are going to receive some reward RTXT, where RT is not known to your algorithm. So this is the bandit setting, the standard bandit setting. The second step is basically, whenever you take this action, it's also going to incur you a vector cost. So CT is some matrix, and depending on what action you choose, you're going to incur basically that column. So that's the vector cost. And you're also given a budget. So your goal is to maximize the total reward which is the standard thing, while making sure that the sum of your total cost, like some norm, like usually people study first the L infinity norm, of the cost that you're incurring is at most B. Like the motivation comes like for many of these bandit applications, choosing different actions does not come for free. Whenever you want to maybe make a change or do something else, choosing an action, that incurs you some cost. So you also have a budget. And the question is, how can you maximize your reward while still being inside the budget? So the problem is also interested in like in a single scalar setting, already in one dimension. But the bandits with knapsack problem is usually, the original paper talked about this problem in the L infinity setting, where you want to make sure that the total cost, the max cost basically, is at most B. And so the original paper was in the L infinity, but then there were extensions. So we know that at least for LP norms, you can get some log competitive ratios. And basically in this paper, we show that, okay, you can actually get again, the same log square D competitive algorithm. So this is not just an additive regret, you're losing some multiplicative factor, so it's so-called alpha regret as it's known in the online learning literature. So it's a log square multiplicative factor that you're losing, and that's what the kind of, and it's, again, you can show a log D lower bound as well, so it's not that you can get a constant. So this is the bandits with knapsack, and again, we also have the proof ideas are somewhat similar, the same inequalities we end up using, maybe with one or two newer ideas. And the results and techniques also extend to some other related problems, bandits with vector costs. Again, I can explain you offline. But so to conclude, this is the high level takeaway, the proofs, there were these 3-4 steps. We started off with this load balancing problem, reduced it to smooth game inequality, then designing gradient stable approximations, and finally gradient stable approximation for a single top K norm. And so as I was saying, there are these generalizations to load balance, other load balancing problems and bandit problems. There are a bunch of open problems. First is, as I was saying, so one question is, can you improve this log square to a single log? Because as I was saying, for L infinity, the lower bound is just a single log, and log square could potentially be improved. We were getting log square by reducing it to top k, and top k to monotone symmetric is again like a log loss. Other second question is actually something which we don't have much of an, actually the first question, yeah, it's also like how to handle arbitrary monotone symmetric norms. Like I don't know how to relax this symmetric assumption. In terms of the challenges, I don't know what's the right kind of like how to break the problem into something simpler. Like top k norms were a good surrogate for symmetric norms, but there's nothing like that known for general monotone norms. And yeah, the other questions are of the form like, okay, how to extend it to other online problems, say like set cover, like some of these other problems. So some problems I know of other results and other techniques, but yeah, I'm happy to talk offline. And finally, I want to conclude with this like broader theme, like besides its direct applications, another reason I find this these optimization problems for monotone norms interesting is because they have lots of connections to these other different looking objects such as XOS functions and packing constraints. So recall I mentioned briefly that any norm or any monotone norm can be thought of as nothing but max of linear functions. And max of linear functions is also actually studied in a lot of combinatorial options and other settings in combinatorial options. They are known as XOS functions. But there you usually think of them as a set function, whereas norms you usually think of as a continuous function. Another third different looking object is like packing constraints, but you can talk about like arbitrary packing constraints. And actually, if you look at the rank function of an arbitrary packing constraint, that's also pretty much just nothing but a max of a bunch of linears. So these three different looking things, and like they're often studied in disjoint from each other. And what would be very interesting is if we can like try to unify them, the techniques as well as the results. And that's something like another reason why I find this direction very interesting. Thank you.
Questions for Sahil?
Yes, Amit.
So in the offline setting, right, there's sometimes these algorithms which work for all norms. They are agnostic of the value of P.
Yes.
Or maybe in top K, you're agnostic of the value of K. So is that something which is possible here? Or?
That's a good question. So offline already, even offline, I'm not sure. Actually, is it known that you can get good? So I mean, offline generally you can get constant comparative rate, like constant approximation ratios. Is it actually agnostic? And so we haven't.
They may depend on P actually, right?
But
one algorithm which is agnostic of the value of P. So the algorithm as such doesn't depend on P.
No.
Cannot get from
Or I think you can get from maybe restricted.
Maybe restricted.
Maybe some special cases, yeah. It seems like somehow you have to be sensitive to what norm you're working with while making such decisions, yeah. I mean, okay, poly D factors are easy, but yeah, logarithmic.
So I assume this fails for like weighted norms, which are not symmetric.
So by weighted norm, I guess it depends how you define it.
Let's say like weighted LP or something.
Yeah, so weighted LP, like one definition could be if I say like the second coordinate, you're going to multiply it by like some, so that's not symmetric.
Right, exactly.
Yeah, but yeah, other notions, yeah, there are other notions as well where you like kind of the largest coordinate you multiply it by some weight, the second largest coordinate you multiply it by some other weight and so on. So those are symmetric, for instance.
But okay, so for the one that fails, which step fails? Is it the approximation by?
So yeah, so actually, so okay, we know like gradient stable approximations always suffice. We don't know how to construct gradient stable approximations for like arbitrary norms.
Yeah.
Okay, for maybe this case, for LP norms, maybe I can do it, but not in general. I don't know how to do it like these weighted scalings. Yeah.
Thanks.
Yeah, hi. So does this also incur log square D for, let's say, L infinity norm? Or
Oh, good. So for L infinity norm, you don't have to go via top K norms. We know directly, like as I was saying, softmax function is a gradient stable approximation, so you can directly work with that. Basically, like the second part of the talk where I was trying to design these gradient stable approximation, that part you don't have to do because you skip that, so you'll save a log, so you get like a single log in some sense. Yeah.
something, but polylog known for symmetric norms only? Or
Polylog-
and D?
Sorry.
For symmetric norms, is it known that we have a polylog approximation?
So this paper basically shows that you can get like a log square D for symmetric norms. Yeah. And yeah, the question is how to go beyond symmetric norms, like to general norms.
Like, is the log square the comparative ratio tight?
So the lower bound we currently know best is the single log lower bound, which is already true for L infinity now. So there is a gap of log square versus log. Yeah, so it's not, I doubt it's tight. I mean, I think it should be improvable.
Other questions? So I have a quick question. So do these techniques have any implications for maximization problems, like maximizing F welfare or something like that?
Good. So yeah, at least the ones, at least we don't know of a very concrete, convincing application. There might be some application which we can kind of cook up, but I wouldn't say like, it's not a very classical application, I would, yeah. So I don't have a good answer for that, yeah.
Yes, sir. If there are no other questions, let's thank Sahil again.